In our next video, we're going to look at what we call the rate of doing work. So in this case, we have a person here who's going to be lifting an object with mass m, and I guess I didn't write down the mass, right? So maybe we'll make it equal to, let's say, 20 kilograms. And he wants to lift it up a certain height at a rate of 2 meters per second, constant velocity. And the question is, how much power does that take? So the question would be, power is equal to question mark. How much force does it require to lift that up, and how much power does that require from the worker? All right, the object is 20 kilograms, and he's going to be pulling on the rope with a force. Now the force has to be equal to the weight of the object. Now you say, well, wait a minute, it doesn't have to be more, because how else can it go up? Well, it's true that if it's sitting on the ground, to get it started, you will have to pull with a force a little bit more than the weight of the object, because obviously you have the gravity pulling down on this mass with a force of mg. So to get it going, you're going to need a force a little bit larger than that. But once you have it moving at 2 meters per second, it will require the exact same force here that is equal to the weight of the object to keep it moving at that constant velocity. That, of course, is the result of Newton's first law that says that once an object is in motion, traveling upward, it will continue in motion as long as there's no net force acting on it. So if the force pulling down is equal to the force pulling up, obviously this is now the tension pulling up, and the tension is caused by the force caused by this person right here, then the object will continue moving up at 2 meters per second at a constant speed. So, definition of power is equal to work divided by time. How much work can you do over time? And of course, work is equal to force times distance. So this is equal to force times distance over time. And of course, the force is the force by which a person pulls. The distance is how much it goes up. And the time is, of course, in how much time that occurs. Now notice that distance divided by time is equal to velocity. So actually, we can say that power required is equal to the force times the velocity of this object. So if the force is equal to mg, and the velocity is equal to 2 meters per second, we simply have to multiply those two. So this becomes mg times v, and so mass is 20 kilograms. G is 9.8 meters per second squared, and that, of course, is 2 meters per second. Now the result of that will be, let's see, 4, that's 40, that's 39.2, that's 300, and 92, what are the units? Well, let's find out. We have meters, second square, meters per second, kilograms meters per second square. What is that equal to? Well, that's newtons. So that's newtons, and then we have meters per second, so that is meters and per second. All right, so now we've narrowed it down a little bit. What is a newton meter? Well, that's equal to a joule, so that's equal to 392 joules per second. And finally, what is a joules per second? Well, that's a watt. That's energy per time, or work per time, so this is equal to 392 watts. And that's the power required for this person to lift that up. Now, how does that compare to horsepower? Well, it turns out that 1 horsepower is equal to 746 watts. So if you do this conversion, we put horsepower at the top, watts at the bottom. 1 horsepower is 746 watts. So what is 392 divided by 746. So 392 divided by 746 equals, that's a little bit over half a horsepower. So that person will have to be quite strong, so 0.53 horsepower in order to lift that object up at a rate of 2 meters per second. So let's say that the person is getting tired by lifting it so quickly. He can reduce the power required simply by reducing the speed. So what happens if he decides, okay, let me lift it up at a slower speed at 1 meter per second, then of course this here would become 1. This would then be half as much. That would only be 196 newton second per meter, or 196 watts, and therefore it only would take a quarter of a horsepower. So you can see how the power that you have available, either in the muscles of the person, or maybe we put a little motor there trying to lift the object up, the rate at which you can lift things up will definitely be determined by how much power you have available. And that's how you do a problem like that.